All right, in this video, we talk about free body diagrams. So your general notes here are free body diagram is a tool that we use in physics all the time, and it's a diagram. So we diagram all the forces that act on an object or a system. An object would be like a pen or a box or yourself. A system of objects would maybe be like a collection of carts or all the objects in a car. Or the solar system. So a system is just a collection of objects that you have chosen to care about for some reason. Um, we represent forces by arrows that point away from the object. So if you are pushing on the object, the force that you're using would be represented as an arrow coming out of the object, pointing in the direction you're pushing on it. And so the arrows are important because they remind us that we study vectors in physics, and all the things we learned about vectors are true. So they have to point in a specific direction, and they also have to, in many situations, have appropriate lengths, meaning if there are multiple forces, you would sometimes be asked to draw your arrows relative to one another. So that the smallest force was the shortest arrow and the largest force was the longest arrow. So that's kind of the general framing of a free body diagram. I didn't forgot to put it in my notes here, but we have kind of a procedure for drawing a free body diagram. And the first part would be to draw a picture. Now, I would say you would draw a picture with the context the object is in. So you'll see that in my examples, but draw like a literal picture of it. Doesn't have to be anything fancy. You've seen my drawings. They're like horrendously simple. Um, just so you can see all of the objects like around the thing you're going to draw the free body diagram for. The next part is actually, I think, really important. Circle the object that you are going to draw a free body diagram for. That comes into play in a couple steps. Start your free body diagram by drawing in the distance forces. So there are some forces that act at a distance. We only know about gravity right now, and so you're going to start all of your free body diagrams by drawing the gravity force in, based on the rules for gravity. The last step, which is the most complex, is to draw all the contact forces. So all the forces we know about right now that are not gravity are contact forces. And those are going to be based on what your circle touches, meaning you will get a sense of what contact forces you need to draw based on the literal things that your circle hits when you draw the circle. And so that's the procedure we're going to go with, and we're going to use this list of forces that we had in the last video. Okay, so we're going to do two examples of free body diagrams before you start your assignment. So first one is sliding a box along the floor. So this is obviously enormous. So maybe we imagine that like I got a new refrigerator and my 3-year-old son is pushing it around the room, just so we get like a general relative height. So I have drawn the picture, as I said, horrendously simple, and I am now going to circle it. So that's step 1 and step 2. Now, a free body diagram, you can draw it as a dot or a box, or you can actually make it the shape of the object. When we get to rotation, we'll kind of modify how we do free body diagrams. But I'm just going to start with a dot. And so we're going to imagine this diagram, the whole point of it is just to analyze forces. And so I am only going to represent the box as a dot. So all the forces are going to be acting on this point in space, which simplifies things a little bit. So next step was to draw in gravity. Based on the orientation of the box on Earth, that gravity force is going to be down. I have no idea the mass or weight of the box, so I am just going to draw an arrow of arbitrary length. So that's the distance force, and so you always want to start with gravity, unless you're in a place in the universe where there's not very much of it, and so you can forget it. But for all other problems, we need gravity. Next up is contact forces. And so here are the forces. Gravity is the force at a distance, and the other 5 are contact forces, meaning something needs to actually be touching the object in order to have these forces exist. And so if I look at my circle, the circle cut through me, and the circle cut through the floor. And so those are the only 2 things in this picture that interact with this object. And so those are the only 2 things that I'm going to draw forces for. So let's start with me because I'm kind of easy. I'm pushing, or actually my son. My son is pushing on the box to the right? So we're pushing a box, not pulling it. So he's on the left-hand side of the box, pushing to the right. That doesn't really fit into a category, so that's going to be just my miscellaneous or applied force. And so I'm going to draw an arrow to the right that represents my son pushing the box. And you can call it an applied force because he is pushing on it, he is applying a force to the box. But basically, that's it. So he's pushing to the right, and that's him. So he's done. Next up is the surface. Surfaces are complicated. There are two surface forces, the normal force and the friction force. The normal force is the perpendicular one. The friction force is the parallel one. So let's do the normal force first. Every time an object is up against another surface, there's a normal force. The surface is horizontal, which means the normal force has to be perfectly vertical. And so Fn is the label for that arrow. And so that's one of the forces. So anytime there's a surface perpendicular to that surface, there's going to be a normal force on that object. The other thing that happens every time you have a surface is friction. Now, there are many, many problems where you are told that something is on a frictionless surface. That's just a way for us to make physics problems a little bit more manageable at first, but friction is always there. Friction operates parallel to the surface, and it always opposes the sliding. And so friction is going to be in the left and right direction. And because my son is pushing it to the right and it's sliding to the right, friction is going to be pushing it to the left. And so my last arrow is going to be to the left, and there's a friction arrow. Now, it's a bit of a coincidence that I have one arrow in every direction. You can have many arrows in the same direction. You can have directions that don't have an arrow. So it's just kind of how this one worked out. So that's the first one, and that describes fully all the forces on the box. Example number 2, swinging from a vine. And so we have me swinging from the vine. Here's the vine. Here's me. Here's like something that it's hanging from, maybe a tree branch, maybe a ceiling. Maybe there's a vine coming from the ceiling, who knows? And so I circle myself, and I draw myself as a dot. And I start with gravity, and gravity is a force that always pulls down on objects. And, we'll get more advanced with gravity later, but it's always down. The only thing that my circle hit was the vine itself. And a vine is a long object that doesn't stretch very much. And so we say tension. Tension and spring are very similar forces. Tension is reserved for long objects that tend to not stretch very much. Spring forces is for long objects that stretch a lot. And so we'll do our own kind of study of springs later in the year. So tension is the one we have. Now the tension runs along the rope. If the rope weren't there, I would fall. And so it's maybe obvious that the rope is holding me up. And the tension has to be directed in the same path that the rope is. So I would draw that arrow off to the side. I didn't really get the angles right. Like this one's pretty steep, this one's more shallow. But you kind of get the idea that the tension goes along the rope and away from the object. And so that would be a complete free body diagram for me swinging from a vine. So there's 2 examples. I'm going to give you a bunch to work on probably in class, and then we'll move on to Newton's second law.